After a stellar intergalactic voyage from the rubber tree power plant planet, Marie decides to drive her sister Deanna and Rita, who is stowed away in the back seat, back to Earth in their minivan, Ol'Smelly. While jamming out to some Bruce Springsteen, Marie drives into a giant telephone pole, which is attached to the Earth, colliding with a force of 3.45 times 10 to the 30th newtons. Assuming that the Earth is at rest with respect to Ol'Smelly and the tremendous trio, that Ol'Smelly has a mass of 1,000 kilograms, and the Earth has a mass of 5.97 times 10 to the 24th kilograms, how much will the Earth accelerate? The first thing we need to know is that Smelly acts on the Earth with an equal and opposite force to that which the Earth acts upon Smelly due to Newton's third law of motion. Some of the important information we need to know is that the force that Smelly acts upon the Earth is positive 3.45 times 10 to the 30th newtons, and that the Earth acts upon Smelly with negative 3.45 times 10 to the 30th newtons. We also need to know the mass of the Earth is 5.97 times 10 to the 24th kilograms. Since we are searching for acceleration of the Earth, we use the equation F equals ma and solve for the acceleration by dividing by the mass. Plugging in the given numbers, we find that the Earth accelerates at a rate of negative 578,000 meters per second squared. This acceleration upon collision is due to Newton's first law of motion, because Smelly is going to continue in the same path unless acted upon by an outside force, such as the Earth.
Part B. Before beginning the voyage home, the radical Rita decides to measure the distance between the minivan on Rubber Tree Power Plant Planet and the Earth. She records the distance as 2.87 times 10 to the 10th meters. If they started from rest, what will their final velocity be before they collide with the telephone pole? Here we see that the mass of the Earth is 5.97 times 10 to the 24th kilograms. The mass of Ol'Smelly is 1,000 kilograms, and the distance between the two is 2.87 times 10 to the 10th meters. The value that we are looking for is the final velocity of Ol'Smelly. The equations we will use to find this value are total initial energy is equal to total final energy, potential energy is equal to negative g times the mass of Ol'Smelly times the mass of the Earth divided by the radius, and kinetic energy is equal to 1/2 mv squared. The first step is to replace the total initial energy with potential initial energy plus kinetic initial energy, and replace the total final energy with potential final energy plus kinetic final energy. The kinetic initial energy is 0, and so is the final potential energy, which leaves us with the initial potential energy is equal to the final kinetic energy. We can plug in negative g times the mass of Ol'Smelly times the mass of the Earth divided by the radius for the initial potential energy, and 1/2 mv squared for the final kinetic energy. The mass of Ol'Smelly cancels out, and we can multiply both sides by 2, which leaves us with v squared is equal to negative 2 times g times the mass of the Earth divided by the radius. This leaves us with a final equation of v equals the square root of negative 2g times the mass of the Earth divided by the radius. Now all that is left to do is plug in our numbers, which gives us with a final velocity of 167 meters per second.
Due to Ol'Smelly's indestructible properties, Marie, Deanna, and Rita can drive away perfectly unharmed from the collision. What was the magnitude of the Earth's initial velocity after the impact? So we know from the two previous problems that the final velocity of Smelly is 167 meters per second, the mass of Smelly is 1,000 kilograms, and the mass of the Earth is 5.97 times 10 to the 24th kilograms. We're looking for Ol'Smelly's initial velocity. In order to do this, we can use the law of conservation of momentum. Because the Earth and Smelly's collision results in an action-reaction pair, their velocities will be proportional to their masses, resulting in equal and opposite momentum. Setting up the equation, we know that the mass of Smelly times its velocity will be equal to the negative of the mass of the Earth times its velocity. However, we won't worry about the negative because we're only looking for the magnitude of the velocity. Solving for the velocity of the Earth, we find that the momentum of Smelly, its mass times its velocity, divided by the mass of the Earth will be equal to the magnitude of the Earth's velocity. Plugging in our numbers and solving for v,
we see that the velocity of the Earth is 2.790292945 times 10 to the negative 20th meters per second. Accounting for sig figs, the Earth's velocity is 2.79 times 10 to the negative 20th meters per second. It makes sense that the Earth moves so slowly because its mass is so huge compared to that of Ol'Smelly's. Thankfully, everyone was unharmed, and the minivan lived to see another day.